the circulation of air. You can see the high pressure is in an anti-clockwise circulation. And our low pressure system is in a clockwise circulation. Now immediately grade 12, what we need to see over here is that this is in the southern hemisphere. High pressure systems moves anti-clockwise, low pressure systems clockwise circulation. Air moves from a high pressure to a low pressure, right? Always from a high pressure to a low pressure, very importantly. Now what we also need to remember over here, when we look at high pressure systems, we can say it's descending air. And when we look at low pressure systems, it is rising air. Okay, very much important. Now, air always moves from a high pressure to a low pressure. Now, when we look at high pressure systems, especially for the learners who found themselves in the interior South Africa, so I'm talking about Gauteng, the Free State, the Northwest Province. When we associate high pressure systems, we think of the Kalahari high pressure system that's situated over the interior of South Africa during winter. If we look at the climatic conditions that we experience, what do we experience? We're experiencing subsiding air. Why? Because we don't see any cloud formation. It's usually cool and dry conditions. Okay, but let's have a look at our questions that's being asked. Now, our first question that's being asked, our first question that's being asked, the above pressure cells are found in which hemisphere? So I just explained to you, definitely in the southern hemisphere. Why? Because we know the high pressure system, the high pressure system turns anti-clockwise. Anti-clockwise circulation, and our low pressure system moves in a clockwise direction. So that we know it's in the southern hemisphere. So all the weather patterns that we might experience in South Africa, high pressure anti-clockwise, low pressure clockwise direction. So our correct answer will be C. If we look at our next question, we just scroll down. Weather conditions associated with high pressure cells are, like I've just mentioned, it's usually going to be dry. Like I've just mentioned, the Kalahari high pressure system. We don't experience any precipitation during winter in the interior of southern Africa, mainly because we have the Kalahari high pressure system above us. And it's usually stable conditions. Now, when we look at high pressure systems, it's sinking air. It creates stable conditions. When we look at low pressure systems, it's usually rising air. It's because of convergence of rising air. So what happens with there? It usually rises, it cools, condenses, clouds, and the formation of precipitation. That depends on the moisture content in the air. So if we look at that correction, 1.1.2, the correct answer will be number 2 and number 3. So our correct answer will be C. Now, if we continue with our next questions, the force that influences the speed at which air travels between high and low pressure systems is going to be the pressure gradient. Now, we've looked at this before. Now, basically, air moves from a high pressure to a low pressure, as known as wind. Now, very importantly over here, right, the pressure gradient, the force that influences speed. Now, we've looked at it. When the isobars are very close to each other, we know it's a steep pressure gradient. Very similar like we've learned in map work. Right, when the contour lines are very close to each other, we say it's a steep gradient. When the contour lines are far from one another, we say it's a gentle gradient. In this case, when the isobars are very close to one another, we say it's a steep pressure gradient. When our isobars are far from each other, we say it's a gentle pressure gradient. So obviously we were experiencing very strong winds. Okay, that's question 1.3. So the correct answer over there will be D. If we move on to our next question, the low pressure system is associated with descending, ascending, converging, and diverging of air. So we looked at it. A low pressure system, right, clockwise circulation of air, we know is rising air. So first and foremost, we know it's ascending, right, and it's usually converging of air, right. Now, we've learned this in primary circulation of air. If you look at, remember in grade 11, we're just revising below here, especially at the ITCZ, the intertropical conversion zone. So what do we find at the equator, right? We have convergence of air, and it creates the equatorial low pressure belt. It's because of convergence of air taking place that it creates low pressure belts. So the correct answer for 1.1.4 will be 2 and 3. So the correct answer will be B. Okay, we quickly move on to our next question. Now, our next question represents a graph. Now, before I'm going to have a look at the questions, just have a look at what the infographic, the graph, provides us with. First and foremost, we have a high pressure system over the interior of Southern Africa. So immediately, when we have a high pressure system over the interior of South Africa, it stipulates usually it's winter, right? And we can identify this high pressure system as the Kalahari high pressure system. Now remember, it's anti-clockwise circulation of air. Now right here on the coast, we can identify a low pressure system, right? And as you can see, the circulation of air is clockwise. Now, like we discussed in the previous question, we established that air moves from a high pressure to a low pressure. And I'm going to write it down there. A high pressure to a low pressure. Now, this is a classic example of berg winds. Because we have the Kalahari high pressure system over the interior of South Africa, and we have a coastal low pressure moving along the coast of Southern Africa. I'm just going to extend my page over here. Now, if I had to go and draw a cross-section of the above mentioned diagram, right, will look something similar to this, right? We have our escarpment and then our plateau, and obviously what happens over here, during the winter we have a very strong subsidence sinking air of the Kalahari high pressure system. And then we have a low pressure system down here at the coastal area. Now, like I've mentioned, air moves from a high pressure to a low pressure. So what happens? The air will move from a higher altitude to a lower altitude. Now, very importantly, what makes South Africa's topography so unique is because we've got coastlines, and then we have the escarpment and the interior situated on the plateau. Now, it's common sense, when we increase altitude, temperature decreases, right? So for every 100 meters we increase of altitude, the temperature will drop with a degree Celsius. But in this case, we have air moving down the escarpment to the coastal regions. So what will happen to this air? It will warm up adiabatically. Okay, so places where the coastal low is experienced are going to experience increase in temperature. Because the air is moving from a higher altitude to a lower altitude. So what's happening over there? As it moves down the escarpment, it warms up adiabatically. For every 100 meters it descends, the temperature increases with 1 degree Celsius. And these are known as berg winds. And it can create uncomfortable conditions, especially down the coastline, right, where temperatures might increase from almost 10 degrees Celsius, a difference. And it can cause veld fires because, especially during winter, if you look at it, our velds are usually dry. So warnings can be sent out when we experience these typical berg wind conditions. So if you look at our diagram, this is just a cross-sectional point of view from it. Now immediately how to spot bergwins. You can see the high pressure over the interior. There's a coastal low, or even there can be a mid-latitude cyclone, because on the end of the day, which we're going to discuss a little bit later on, a mid-latitude cyclone is a low pressure system. Okay, but let's have a look at the questions that's being asked over here. Okay, the temperature and moisture content associated with pressure cell C is going to be, so it's going to be cool temperatures, right, and it's going to be low moisture. Let's have a look back. Let's just go back to this diagram. There's C situated over there. I just want to get my eraser. Now, why do you think they've asked the moisture content? Very importantly, once again, we're going back discussing, right, we're revising climate. So over here, what do we have? We have the cold Benguela current. So the cold Benguela current creates cool and dry conditions, especially on the west coast of southern Africa. Now, if you can remember what we learned in grade 10, on the east coast of southern Africa, we have the warm Mozambican current, right? Comes from the equator, and it creates warm, moist conditions on the eastern coast of southern Africa, whereas the Benguela current comes from the polar regions. Now, if we go back to our question, just want to get my pen here. If we go back to our questions and we look at the questions that's being asked, describe the air temperature at cell C. So it's going to be cool and dry because of the cold Benguela current. So if we look at the answer over here, go to our next slide, right? Cool temperatures and low moisture. So the correct answer is going to be 2 and 4. So D will be the correct answer. If we move on to our next questions, place M, P, S, or H will experience bergwins. Now in this case, the correct answer will be C. Because as we can see, right, the air moves from the high pressure to the low pressure. That will be the correct answer, creating uncomfortable conditions at this low pressure system right over there. Let's move on to our next question. Pressure cell D is associated with, so let's just go back to our diagram to see what's pressure cell D. Now, as you can see, pressure cell D is a low pressure system. Now very importantly, once again, we have different ocean currents down there. We have the warm Magalhães current, Mozambique current. So there's warm moisture over there. So the correct answer for that question, it will be fog and drizzle, D. Okay, so that answers our questions on bergwins with the type of diagram that is provided. Our next question that I want to have a look at is the Kalahari high pressure system. And the diagram which are shown shows typical conditions during winter. And I will explain in a second why it's winter. Now very importantly, when we look at this diagram, on the one side we have two graphs. The one side there's a graph, if you can see it, there's a graph representing altitude on the vertical axis, and the horizontal axis we got temperature. Now very importantly, right, as you can see, the temperature decreases with altitude. So I'm just going to make it that decreases with altitude. Now grade 12s, that is normal, right? Let's say for instance I go and climb Kilimanjaro. What's going to happen with the temperature when I reach the summit? The temperature is going to drop. So in this case, if you look at this graph, the temperature is decreasing. We also refer to that as a normal lapse rate. Then right over here, we can see that the temperature is increasing. in temperature. And we know the correct concept to be used is an inversion layer. Inversion is when there's an increase in temperature with an increase of altitude. So it's not usually normal, but we're going to have a look at it in a second. And then once again, just above the inversion layer, there's a normal lapse rate where the temperature is decreasing. Now coming back to our image of this cross-section in the eastern half of the country, the reason I've claimed that this graph or cross-section represents winter is because our inversion is below the escarpment, as you can see. The reason why it's below the escarpment is because of a very strong subsidence from the Kalahari high pressure system, as you can see these arrows. Because the Kalahari high pressure is much stronger and much more prevalent during winter. So there's a strong subsidence of air on the plateau. Now what happens at sea? We know this happens on the eastern side of southern Africa. So once again, the warm Mozambique current comes into play over here. As you can see, it's on the east coast of southern Africa. This is warm, moist air. Coming in, converging to the interior of southern Africa. But this warm, moist air can't reach the interior because of the strong subsidence of the Kalahari high pressure, creating the inversion. So as this warm, moist air rises, obviously what happens with it? Temperature decreases. Now what happens over here? The inversion, it can't go through the inversion because there's a strong subsidence from the Kalahari high pressure system. And once again, now obviously you can see the temperature decreasing, right, because of adiabatic lapse rate. Now, just for the sake of it, this diagram I will answer those questions in a minute. If you look at the diagram, what will it look like during summer? Right, there's our escarpment, right? Let me just move further down, sorry. Okay, so here's our escarpment. Now, what's prevalent over here, what we'll notice, is that the Kalahari, the inversion is way above the escarpment. There's the inversion. Why is this way above the escarpment? Because the Kalahari is extremely weak. It's a weak subsidence. From the Kalahari high pressure system. Now, in order for this to happen, it means those moist air coming in from the Indian Ocean, the warm Mozambique current, right? There's no inversion blocking it. So all this moist air can reach the interior. And obviously we experience much warmer temperatures in the interior of southern Africa. Now, there's warmer temperatures creating low pressure systems, the air rises. Now, but very much importantly, that air that comes in that used to be blocked by the inversion layer, right, consists of a lot of moisture, right, and it rises. And it can move over the escarpment onto the plateau. And because of the warm summer temperatures, what happens? That warm air cools, condenses, clouds, and rain. And we experience rain during summer months in the interior of southern Africa. Now, going back to my diagram, just to answer the questions. If you look at question 1.2.1, the pressure cell responsible for the descending air in the interior marked X on the diagram. So we already discussed it. It's the Kalahari high pressure system. The area marked B, let's just go back to our diagram. That's our inversion. So the correct answer will be Y. The temperature at sea, right? Let's just have a look at the temperature at sea. Okay, there you go. What's going to happen with the temperature at sea? As it rises, like I've mentioned to you, what happens when we go up with altitude? The temperature decreases. So our correct answer will be the temperature at sea will decrease as altitude increases. The diagram represents winter conditions. The simple reason why is because we looked at this diagram, we can see the inversion is below the escarpment. There's very strong subsidence from the Kalahari high pressure system, blocking out the warm, moist air coming from the warm Mozambican current and the eastern half of southern Africa. So the correct answer is there, that represents winter. The possibility of rain over the interior, because the inversion is below the escarpment, it will be low. 1.2.6, the descending air from the plateau will warm as it ascends. Now this is very important, right? We got descending air, sinking air. Now, a typical example in the interior of southern Africa is our mornings are extremely cold, covered with frost. Well, what happens? It warms up quite nicely up to mid-teens, low 20s. So it warms up adiabatically as the air sinks, right, creating these mild winters, dry winters in southern Africa. Okay, so the correct answer over there will be warm. The reason for the descending air temperature change is due to adiabatic warming. Okay, and the moisture and temperature content of the air at mass sea, let's just go back to our diagram to determine that. At sea, as you can see, it's going to be warm and moist. So if you look at the correct answer, the moisture and temperature content of the air mass at sea is going to be warm and moist. So that basically explains the Kalahari high pressure system, the influence it has on us, especially over the interior and on our coastal regions regarding rainfall, precipitation during summer rainfall and no rainfall during winter. Okay, let's just move on to our next question. And our next question is what we're going to discuss. We're going to have a look at mid-latitude cyclones. Now, the reason why I can identify this as a mid-latitude cyclone is, great Charles, this is vitally important. Remember, when we look at mid-latitude cyclones, consist of two fronts. We're dealing with a cold front and a warm front. Okay, do not confuse between tropical cyclones. When do we experience mid-latitude cyclones? Mostly during winter, right? Very important phenomenon for us because it brings much needed rainfall to the southwestern Cape areas, right, where we experience a Mediterranean climate. How can I identify this as a mid-latitude cyclone? So let's quickly have a look at our diagram. Right, first and foremost, right, we have a cold front. Now, a mid-latitude cyclone consists of a cold front and a warm front. Now, from a synoptic point of view, this is what it will look like. I'm just going to extend my payload over here. This is our cold front. And attached to it is our warm front. Now, this is just a cross-sectional point of view that's been given to over here. Now, very importantly over here, we're dealing with three different types of air masses, right? The cold front is the leading edge of cold air. So think of it this way. Where the cold front is, the air behind is going to be cold, right? Where the warm front is situated, the air behind the warm front is going to be warm. The air in front of the warm front is going to be cold. Very importantly, when we look at this, right, there's the cold front. As you can see, the movement that's been shown over here, direction of movement, it moves from west to east. Why does it move from west to east? Because it moves in the westerlies wind belt. space over here. Now, these mid-latitude cyclones usually comes in families, cyclogenesis, that we discuss, right? So as you can see, remember, the cold front is the leading edge of cold air. So as you can see, we experience cold conditions over there. This is warm air. So this is also cold air that we experience in front of the warm front. Keep in mind, grade 12s, we seldomly experience warm front conditions in South Africa. It's mainly the cold front that affects us. The warm front is usually too far down south, so we only experience the brunt of the cold front, right? That leads to thunderstorms in the southwestern Cape. Now, by now you should know that a cold front, right, cold air is much denser than heavier than warm air. So as this cold front moves west to east, it's almost like cowboys and crooks. It's inevitable that the cold front is going to catch up with the warm front, right? The warm front is much more stationary than the cold front. So as the cold front approaches to the warm front, right, as you can see, the cold air approaches. What does it do with the warm air? It forces this warm air to rise. And when this warm air forces to rise, it cools, condenses, clouds, and rain. And very importantly, as you can see, we experience cumulonimbus clouds, as you can see. Right? So this experience a steep pressure gradient. Right? Steep pressure gradient because this cold air, the cold air forces this warm air to rise. Right? And where this warm air is being forced to rise, we experience immediate condensation, cloud build-up, and rainfall in the form of cumulonimbus clouds. So when we look at the warm front conditions, right, as you can see, it's almost like the cold air just glides over the warm air just glides over the cold air. So there's no steep pressure gradient over here. So most of the time at the warm front, we experience calm conditions with soft rain, usually with nimbus stratus, associated with nimbus stratus type of rain. Whereas we look at the cold front, we experience cumulonimbus clouds because there's a strong upliftment of the warm air, forcing the warm air to rise. Now, very importantly, it moves from the west to east. Right. Now let's have a look at some of the questions that's being asked. Okay, give evidence from the diagram that Z shows a cold front. Now, first and foremost, right, it's a very steep gradient. And we can see, most importantly, there's cold air behind it. There's cold air behind the cold front. Like I've just mentioned, where's the leading edge of cold air? Right? The cold front is the leading edge of cold air. So the air behind is going to be cold. In the case of it's a warm front, what's going to happen? All the air behind the warm front is going to be warm. So the cold air is behind the cold front. That's what we can mention over there. Now, very importantly, we can also see the cloud buildup. It's cumulonimbus clouds. And that's associated with cold front conditions. Now, very importantly, right, what happens after that? Why do cumulonimbus clouds develop along the front Z? Now, first and foremost, is because the cold air undercuts the warm air. Right, as we look back at our diagram, you can see it, the cold air, as it moves from west to east, it's going to undercut this warm air. And the only place where this warm air can go is up, right? And it's a strong upliftment. It's like almost convection going up. And it's a rapid rise of warm air. So we can also mention that, right? There's rapid upliftment happening right? The warm air is forced to rise. And then obviously, as soon as it rises, it cools, right? There's a huge amount of condensation taking place, cloud buildup takes place, and eventually it would lead to rain. So we can just add over there, right? Large scale of condensation taking place. And lastly, the steep gradient causes rapid upliftment. Now, the next question, I'm just going to explain on the diagram itself. And the question states, once the cold front passes over, air pressure will increase. Explain why this is the case. And I want to go back to the diagram. I just want to get my eraser over here. Now, remember, this cold front moves from west to east. And this will be the movement over the few hours. Right, now immediately as the cold front moved over, what just happened? All the warm air has been displaced. So where will we find the coldest air? Closest to the surface. So immediately when that happens, the pressure will decrease. Now remember, our first question, just the basics, and that's the reason why I added that question. When we look at high pressure systems, it's usually descending air. We associate it with cold air. So that's going to be closest to the surface. So immediately what's going to happen? The pressure is going to decrease. So we can just add that to our question. All right? The cold air is heavy. And dense, and all the warm air has been uplifted, increasing that pressure. My apologies, increasing the pressure. Now our last question on mid-latitude cyclones. Account for the direction of movement of the phenomena. It moves from west to east in the westerlies wind belt. Sorry, we do still have another question regarding this topic over here. Now, if you look at the next question, they ask us, with reference to the diagram, write a paragraph approximately 8 lines in which you explain the development of a cold front occlusion. Now, like I've just mentioned, when we look at mid-latitude cyclones, it consists of a cold front with a warm front. It's inevitable that the cold front is going to catch up with the warm front. And when it does, we call it the occluded stage. Now, we have 2 different types of occlusions. We have a warm front occlusion and a cold front occlusion. And I'm going to explain both to you in the next couple of minutes. Now, the easiest way to explain this to you is drawing 2 diagrams, explaining to you a warm front occlusion and a cold front occlusion. Now, first of all, the question stated that we should explain a cold front occlusion. So let's do a cold front occlusion first. Now, like I've mentioned to you, it's when the warm front, cold front is caught up with the warm front. Now, very importantly, I said to you, when we deal with mid-latitude cyclones, you know, we're dealing with 3 different types of air masses. So we know that's my cold front. Now, when the cold front is caught up with the warm front, right, there's the warm front. So right over here, we're dealing with 3 different air masses. 1, 2, and 3. Now the cold front moves west to east, right? It's caught up with the warm front. Now what happens with a cold front occlusion? The air behind the cold front, I'm going to write it, very cold, is colder than the air in front of the warm front. So I'm just going to write it cold. Now obviously the cold front is caught up with the warm front, so what has happened? All the warm air has been displaced upwards, am I correct? That's the warm air. And interestingly enough, when we have a look at it, easy to identify, distinguish between the two of them. Have a look at it. The cold front attached itself to the surface. The simple reason why is because the air behind of the cold front is colder than the air in front of the warm front. Now, obviously, if you think of it, where will the coldest air be? Right? Closest to the surface. Am I correct? And that's the reason the cold front attaches itself to the surface. Remember, all the warm air has already been displaced. But the air that was in front of the warm front wasn't as cold as the air behind it. So, as you can see, right, the cold front attaches itself to the surface. Right? Not only does the cold front undercuts, right, all the warm air in front of the warm front, but also undercuts the air in front of the warm front. Right? The warm sector, as you can see, has completely been uplifted, right? Completely. And the simple reason why is because the cold air moves faster than the warm air. Now, let's say, for instance, they've asked you a warm front occlusion. Okay. Let's just quickly take a short break, and then we'll get back to it explaining warm front occlusions. See you in a bit.
Did you know that spotted hyenas are one of the few mammalian matriarchal societies? The social system of the spotted hyena is openly competitive, with the larger females dominating the smaller males. Even the lowest ranking females are dominant over the highest ranking males. Spotted hyena societies are similar to that of primates with regards to group size, structure, competition, and cooperation.
Want to catch up on some of your studies? Join Mindset for late night studies. Monday is mathematics, Tuesday is physical sciences, with life sciences on Wednesday and accounting on Thursday. Friday is English, maths literacy on Saturday, and Sunday's a good day to catch up on geography. Every day from 9 p.m. till midnight, and again from midnight till 6 a.m. Late Night Studies, only on Mindset.
Welcome back. Once again, I'd just like to thank you, our sponsors, Liberty, and you guys at home, the Tenfold Education app. Go and download it. Lots of goodies on there. And then go and give us a follow and a like on YouTube at the Mindset Learn channel. Once again, a lot of good stuff happening over there that will benefit you with the exams. Now, coming back to our question regarding warm front occlusions. I've just explained the cold front occlusion to you, right? Most importantly, the cold front attaches itself to the surface. Why? Because the air behind the cold front is colder than the air in front of the warm front. Now, it's basically vice versa what happens with the warm front occlusion. When the cold front eventually caught up with the warm front, right? The air behind the cold front is not as cold as the air in front of the warm front. Now, once again, remember, all your warm air has been displaced, right? So what happens over here? As you can see, the warm front attaches itself to the surface because the air in front of the warm front is extremely cold. So we will find the coldest air closest to the surface. Hopefully that will explain the cold front and warm front occlusions to you guys. Now, our next question that we're going to discuss, and I chose this question because we're usually being asked about tropical cyclones. Now, tropical cyclones is a phenomenon that happens right over the world. Now, they're quite devastating. There's nothing quite good about them. A lot of damage being caused environmentally, socially, and economically. And I've chosen a tropical cyclone, but I've chosen Hurricane Helene. Now, a tropical cyclone, we in Southern Africa, we call them tropical cyclones. If you live in America, we refer to them as hurricanes. If you live in Japan, Asian countries, it's known as typhoons. But on the end of the day, it's all the same thing. Just remember, a tropical cyclone is a low pressure system, right? It's rising air, rapidly rising air. And we're going to have a look at the formation, why it takes place. But keep in mind, if you might get a question when they ask about hurricanes, remember it's in the northern hemisphere. So those low pressure systems moves anti-clockwise, whereas tropical cyclones moves clockwise in the southern hemisphere. Now, if you look at the infographic that's been given to us, a tropical storm and storm surge watches have been issued next to Florida's southwestern coast. Florida is a state in America. Wind speeds up to 35 miles per hour over the southeastern United States. Hurricane Helene is expected to produce a total rain accumulation of 3 to 6 inches. Now, from a synoptic point of view, we always look at a tropical cyclone. It's got an eye, right, and usually almost perfectly shaped round isobars. Now, we know in the southern hemisphere they move east to west in the tropical easterlies. And when they do recurve, it's because they move into the westerly wind belt. We know for a fact that tropical cyclones formation can't take place between 0 and 5 degrees from the equator because it needs the Coriolis force, right, to be able to move. So anything from between, if you look at the formation of tropical cyclones, it's usually from 5 degrees up to 20 degrees north and south of the equator, right? And most importantly, always over warm ocean waters. But just have a look at this infographic that's been given to us, which we can discuss. Right, you can see the hurricane over there, and what to do after. They've mentioned avoid flood waters, wash your hands frequently, wear enclosed footwear, drink bottled water, use purification tablets or boil for 1 minute. Right, and this is just precautionary measures to take place, what we need to do when you're being affected by a tropical cyclone or a hurricane in this case. Now, if we look at our first questions, where do hurricanes occur? Now, the name hurricane obviously refers to tropical cyclones that happens in North America. Okay, just a different name for it. And if you look at our next question, our next question stated, okay, where do hurricanes occur? North America. If we look at our next question, explain factors necessary for the formation of Hurricane Helene. So, not only for Hurricane Helene, any tropical cyclones. Now, when we look at tropical cyclones, first and foremost, right, we name them alphabetically. Now, in the case of Hurricane Helene, right, we can go through it. It's A, B, C, D, E, F, G, H. So it means it's the 8th tropical cyclone or hurricane for the season. So, hurricane for the season. And we can also mention, right, if you look at the formation, ocean temperatures above 27 degrees Celsius. Now, usually when we experience these ocean temperatures above 27 degrees Celsius, is usually late summer, early autumn. Now, a simple example I tend to use in my classroom, if you think of it, right, you experience 6 months of beautiful weather, summer. When are we going to experience the highest ocean temperatures? Usually late summer, early autumn. So when we look at the formation of tropical cyclones, key ingredient over there is ocean temperatures above 27 degrees Celsius. We need a high moisture content. Right, and high humidity. Now, very important as well, they rely on latent heat. Now, what is latent heat? It's the heat being released when condensation takes place. Now, obviously, if you look at the process of evaporation, water turns into a gas. Now, when that gas rises, right, and that gas turns back into a liquid, right, that's known as condensation. And latent heat is being released when that condensation is taking place. We need unstable air, so that's rising air. And most importantly as well, we need little surface friction. So we need beautiful conditions, right, taking place above the ocean. Okay, now if you look at our next question, now according to the infographic, there are things to do after a hurricane. Explain how these practices can limit injuries and save lives. Now, before I'm going back to the infographic, right, we need to have a look at the following: economic, environmental, and social social impact of these storms. I just want to outline these because they are extremely important, grade 12s. In all honesty, there's nothing nice about tropical cyclones. It creates a hell of a lot of devastation, right? And heartbreak as well. We're talking about wind speeds up to 250 kilometers per hour. We experience exceeding rains of almost 80 to 100 millimeters of rain over a very short period of time. Now, if you just think of this, the magnitude of the storm that we experience, you think of a lot of rainfall, you experience storm surge, wind speeds exceeding 200 kilometers per hour. It's going to create a lot of damage. Now, especially if you look at on the eastern side of southern Africa, where a country like Mozambique is quite prone for tropical cyclones, the devastation is enormous. Now, if you look at the economic impact of these tropical cyclones, it can lead to unemployment, right? Can lead to businesses closed down. But also farmland, agriculture, farming destroyed, cattle destroyed. Right, and the cost of infrastructure rebuilding is going to be absolutely massive. Right, so economically it's not viable whatsoever, right? Creates a huge amount of damage. Environmentally, we can also mention, right, with the storm surge being experienced, we're going to experience soil erosion. We're going to experience flooding. So topsoil are being washed away, fertile land is being washed away. Right, environmentally it can cause deforestation. It can disrupt ecosystems and food chains. And lastly, when we look at social impacts it can have on social impacts on the communities, on the people, it can injuries, diseases such as cholera, especially after the tropical cyclone. It pollutes our water, right? And it can also cause food insecurities. Now, please remember, when this question is usually the paragraph question that might be asked in the final exam, just remember to categorize the difference between economic, environmental, and the social impacts that these tropical storms have on a community. Okay, now the last question, right, account for the name given to this hurricane. So we saw the name was Helen, right, so we know Helen, just counting back quickly, it's A, B, C, D, E, F, G, H. So it's going to be the 8th hurricane for the season. Because we name them according to the alphabet. And then if you look at our last question, according to the text, what weather elements could cause destruction in the area? Now, weather elements, flooding, storm surge, increase in waves because of the wind, and strong winds. So these weather elements can cause a great amount of destruction over a very short period of time. Unfortunately, that's all we have time for today. Good luck for tomorrow's paper. I'll see you next week for paper 2. Ciao.
out to everybody at home. Welcome to Q&A with myself, Lingilek Amazibuko, and you guys are in for a treat. We are doing electric circuits, and it's all for you grade 12s. So I hope that you guys are energetic about this. I hope you guys are ready and amped up for this session. It is going to be super amazing, trust me. Well, instead we've got John, who will be tackling the topic for us. Yay! Isn't that so exciting? Hi, John.
Hi, Lungi. Great to be with you this evening and with you too. And I know it's the first day of school, but you've got lots of work to do this term. So let's get straight into it because we're going to be starting with electric circuits. Now, many of you have done electric circuits in grade 11, and maybe your teacher won't have time to go over them because you're starting machines and all these other things that relate to electric circuits. So please make sure that you give Lungi a message about things that you're not sure of. So where can they post things and do stuff?
Everything can be posted on our Facebook page. That is www.facebook.com/MindsetTV. And if you've got those juicy questions that need like a whole lot of explanation, hit us up on our emails. That is questions@learn.co.za. Guys, please prepare yourselves for the prelims coming up. We do not want any failures. As I always say, the only thing that I want is distinctions, nothing but distinctions. So make sure that you guys ace your prelims coming up sometime this year. So
yeah, it's soon. It's the end of August.
Really?
Yeah,
That's
about
soon.
the 25th of August. So
So you guys have got like a few weeks, not even a month.
It's like 4 weeks.
Sure.
Yeah, you really need to focus now. Okay, so let's get going. Can we get going? We don't want to run out of time. So guys, we're going to start straight away by hitting up a little question here on a circuit that's straightforward so that we can get through the basics. In the meantime, I want you, if you've got any question, now's the time to ask. You're not sure of a definition, you're not sure how to do something, ask now. Don't leave it until later. Okay, so without further fuss, let's go and have a look at this question here. There is no internal resistance in this question, in this circuit at least. So we're going to do a really basic question, and we're told initially that there's no internal resistance. So that value there across the